All right, so we have these three true-false questions right here. This is question one, parts A, B, and C. All right, so with A and B are both n by n invertible, and we want to know about the inverse of AB. Now, we probably learned maybe in class or something that the inverse of a product is the product of inverses, but we can't forget to swap the order. Um, So if you forgot this fact, this more or less shows us that this is probably going to be false. Now we might want to come up with a counterexample to ensure that it's actually false. But first, let's actually prove this, and then we can be pretty positive that this won't be true. So what is the inverse again? So the inverse of a matrix is another matrix that we have to multiply our matrix by in order to get the identity. So if AB inverse is B inverse A inverse, then we should have AB inverse times B inverse A inverse equals what? What should go here? This should be the identity matrix. So if this is true, then this should certainly be true. But we can check this, we can verify this. The nice thing about matrix multiplication is that we can freely associate the parentheses sign. Sorry, this should just be AB. The inverse is something that we multiply our matrix by to get the identity, right? So we can verify this by just showing that this multiplication equals the identity. Well, the way that we're going to do that is we're going to associate the parentheses how we want to. So let's just sort of drop the parentheses. So this is A, B, B inverse A. But we can put the parentheses where we want, right here. So what's B, B inverse? Since B inverse is the inverse of B, B, B inverse must be equal to I. So this is A, I, A. This should be an inverse. This should be an inverse. A inverse equals I. So what did we just show? We just showed that when I multiply AB times B inverse A inverse, we get the identity. This actually automatically implies that AB inverse is B inverse A inverse. Okay? So this is a powerful concept. All we have to do to show that something is the inverse of something else is just multiply them together, and if it's the identity, then they are inverses of each other. If you don't get the identity, then they're not inverses of each other. It's really that simple. So that's a really powerful concept. So using this, we're going to say that this is probably false. It's definitely false. I would encourage you to, on your own time, maybe find a counterexample where you have A and B, multiply them together to get the matrix AB, and then take A inverse, B inverse, multiply them together, and then take AB and AB and A inverse, B inverse, multiply them together. You probably won't get the identity matrix. So this is false. All right, so now for B. So B is asking, A is n by n, Ax equals B has at least one solution for every B in Rn, then the solution is unique for every B in Rn. So let's parse through the statement. So A is square, it's n by n, it's square, that's going to be important. Ax equals B has at least one solution for every B in Rn. So what should this remind us of? This first part of the statement has a solution for every B in Rn. This should remind us of onto transformation. So if t goes from Rn to Rn and t of x is Ax, with this matrix A, that's n by n, and satisfies this part of the statement, then T would be onto. So that just pointing out that we should remember that fact. So T is onto. We're going to remember that if AX equals B has at least one solution for every B in Rn, that means A must have pivots in every row. A has to have pivots in every row. We've gone over this several times, but whenever you are guaranteed to have a solution, that means you have to have pivots in every row. So we also have that the transformation is onto. So let's look at the next part of the statement. So does the solution have to be unique for every B in Rn? So since it's square and we have pivots in every row, that also means we have pivots in every column. So does that mean the solution has to be unique for every B? That sounds true. Now why do I think that's true? So let's say we're solving AX equals B. Let's imagine the augmented matrix that we would set up to solve this problem. So we would have A on the left side, B on the right side. Now A has pivots in every row. There's no row of zeros at the bottom of the echelon form. But since A is square, we also have to have pivots in every column. So when we row reduce this to RREF, it's going to look something like 1, 1, 1, zeros everywhere else on the left side, and something here in this column that's going to tell us what the solution is. And since there's no free variable, your solution is exactly going to be like x is whatever you get on the right side. There's not going to be any sort of like parameter times vector plus constant term. This isn't going to happen because since there's no free variable, that's what the free variable is what would create this term. So you're just going to get a unique solution. Okay, hopefully that makes sense. So finally, A is n by n, and AX equals B has at most one solution for every B in Rn. Then that solution must be unique for every B in Rn. So I'm not a huge fan of the wording in this question because I'm not sure whether or not we're supposed to consider whether or not there can be no solution. But I'm going to assume that when it says must be unique for every B, I'm going to assume that means that it's telling us that it has to like exist for it to be unique. So I'm interpreting this as must have exactly one solution for every B in Rn, and we're not going to and we're going to assume that it's not allowing for no solutions. Okay, so A is n by n, AX equals B has at most one solution for every B. So this first part, from here to here, having at most one solution for every B, what should that remind us of from last week? That should remind us of one-to-one. One-to-one means that you don't have, it means you never have multiple solutions. Never have multiple solutions for T of x equals B, which is equivalent to AX equals B. And if we look at this definition, that tells us that we have to have pivots in every column. Of A. So A is n by n, AX equals B has at most one solution for every B. So we have to have pivots in every column of A, but once again, since A is square, that means we have to have pivots in every row. And now we can answer the question. So Do we have a unique solution for every single b in Rn? Once again, we're going to be in this situation where we have A, B, pivots in every row and every column. And the solution that we get for Ax equals b is exactly the augmented column of b. And so I think the answer would be true. The answer is certainly true. If Ax equals b has at most one solution for every b in Rn, that means that the solution must be unique for every b in Rn. So very similar to part B. So these are the first three true falses. So two more true falses, D and E. So if A and B are invertible square, then A plus B inverse is A inverse plus B inverse. Also, part of the question was, is A plus B even invertible in the first place? So this is going to be false. Actually, because A plus B is not even guaranteed to be invertible in the first place, and so we can't write that it's equal to something that's defined when it's not defined. So let me show you a counterexample that shows why A plus B is not even going to be invertible. So for a counterexample, we're going to need A and B to both be invertible, but we're going to want their sum to no longer be invertible. So I think the easiest example that does this is A is the identity, and B is also the identity, but we're going to change it to be -1 times the identity. So we should agree that A and B are both invertible. If you're not sure why A and B are both invertible, well, the identity matrix clearly is invertible because I times I is I. So the inverse of the identity is itself. And B is invertible because also B times B is going to be the identity matrix. So B's inverse is going to be itself. If you're getting lost by what I'm saying right here, you can also just remember that a matrix is invertible if it has pivots in every row and also in every column. The pivots in A are here and here, so yeah, here and here, so yeah, they're both invertible. But look what happens when we add them. A plus B is 0, 0, 0, 0. This is the zero matrix. So if A plus B inverse were going to be A inverse plus B inverse, then we would certainly want A plus B to be invertible. But A plus B is not invertible. The zero matrix is not invertible. If you're wondering why, once again, you can see it doesn't have pivots in every row and every column. It doesn't have any pivots. But also using the sort of textbook definition of invertibility, if the zero matrix were invertible, we would want 0 times C to be equal to I for some C. C would be the inverse of 0. So we're going to sort of assume that it is invertible and show the contradiction. So if 0 were invertible, then there should exist some matrix that we can multiply it by to get I. But 0 times any matrix is 0, so this implies that 0 is equal to the identity. 0, 0, 0, 0 is certainly not equal to 1, 0, 0, 0. So this is a contradiction. This contradiction tells us that 0 is not invertible. Any way you look at it, that's going to be true. So this is certainly false because A plus B inverse might not even exist. So it's not going to be equal to two things that do exist. Okay, false. Next, A is 3 by 4, B is 4 by 2, ABX. So we want to know the domain and codomain. I think this is a good problem because it's going to allow us to review the rules of matrix multiplication. So A is 3 by 4. So let's just sort of draw what A looks like. So A is going to look like this. 1, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3. B is 4 by 2. 1, 2, 3, 4. 1, 2, 3, 4. So this is A. This is B. This is good because we should have learned that for matrix multiplication to be defined, we need the number of rows in the first guy to equal the number of columns in the first guy equal the number of rows in the second guy. Another good way to see it is that A is 3 by 4, B is 4 by 2. So these numbers have to match in the middle. And then what a lot of students learn is that these match and then sort of cancel. And what you're left with is on the outside. So the product of these two matrices is going to be 3 by 2. 1, 2, 3, 1, 2, 3. So this is what AB is going to look like. Okay? But we want to know about the transformation defined by AB. So T of x is ABX. So the input of this transformation is this x, which goes here, and then we multiply it by AB, and that's the output. T of x is the output. Okay? So let's think about what size the inputs and outputs have to be. So if I'm going to multiply AB by a vector x, what size does it have to be? Well, we need the number of columns in this guy to match the number of rows in this guy, so this has to have 2 entries. And then when we multiply these two guys together, we're going to get the number of rows of AB. So it's going to be a vector like this. And so remember that AB is 3 by 2. So x has to be 2 by 1. And then T of x has to be 3 by 1. Okay? So this is what I'm trying to show here. This is how you would see it sort of algebraically. So the domain of this transformation is the size of x. So this is the domain, is R2. And the size of the output is going to be the codomain, R3. So now we just have to check, is that actually what the true-false said? No, the true-false said that the domain was R3 and the codomain was R2, so it's sort of a trick question. They wanted us to get it backwards and say it was true, but this is certainly false. I also just want to remind you that another way that we could have thought about it, was before multiplying A and B together, we can think about the transformation as being like starting with x, multiplying by b, and then multiplying by a. So x starts here, then we multiply by b, then we multiply by a. So let's follow what that would look like. So a, once again, is 3 by 4. 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is A. This is B. B has to be 4 by 2. 1, 2, 3, 4. 1, 2, 3, 4. And then x has to be some vector. This is going to be A, B, x. And this is all going to equal T of x, which is also going to be some vector. So let's kind of follow what size the vector is going to start and end. So first we're going to multiply by b. So it has to have the same number of rows as b has columns. And then bx is going to be a vector with 4 rows. So it's going to have 4 rows. 1, 2, 3, 4. And then we're going to multiply this vector by a. This has 4 rows. This has 4 columns, so that works. So then this matrix times this vector is going to be 3 rows. Once again, the input is R2 and the output is R3. So just a slightly different perspective thinking about this problem, following the size of x as we first multiply it by b and then multiply it by a. So this is number 2. So A is n by n, B is n by m. Part A, x is in Rm, ABX must be in which of the following subspaces. So I think the strategy for this problem is going to be to sort of just look at the size of x, look at the size of AB, and then finally look at the size of the vector ABX. So let's just sort of draw A. So A is some sort of matrix. B is some sort of matrix. This is just not to scale at all, obviously, but just sort of want to picture it. X is going to be some sort of vector, and they're all going to be equal to some sort of vector. So this is A, this is B, this is X, this is ABX. So let's write down the size of these guys. So A is m by n, so m rows, n columns. B has n rows and m columns. So what size does X have to be? If it's a vector, X has to be m by 1. And then ABX, if you think about it, it's m by 1, and then it's going to be size n, and then it's going to be size m again, so it's going to be m by 1. And this makes sense because AB has to be size m by m, right? Because A is m by n, B is n by m, so that's going to create m by m, okay? So if X starts in Rm, ABX also has to be in Rm. All right, so now which of the subspaces does it have to be in? Well, we can definitely eliminate a few of them. So null A is a subspace of Rn because A has n columns, and remember the null space are vectors x such that Ax equals 0, and so any x satisfying Ax equals 0 has to have the same number of entries as columns in A. So this has to live in Rn. So we can certainly eliminate it. Col B is going to live in Rn because B is n by m. So any linear combination of the columns, so let's say I take linear combinations of these columns in B, any linear combination of these columns is certainly going to have the same number of entries as the columns do. And the columns each have n entries. So col B is a bunch of vectors in Rn. Okay, so we can also eliminate it. Now null B, if ABX were in null B, that would imply that B times ABX equals what? And what is null B? Null B is vectors such that B times the vector is 0. So if I'm saying that ABX is in null B, B times ABX has to equal 0. Now, is there any reason to believe that this would be true? I don't think so. So I don't think we can really conclude that it is. So let's sort of forget about that for now. Maybe put a question mark here. Probably not, right? But col A, let's look at that. So col A is, if you're in col A, that just means that you're a linear combination of the columns of A. But let's look at this multiplication. So we start with x. We then get bx, which is going to be some vector in Rn. And then we're going to multiply that vector by A. But we think about A times bx. Put parentheses around bx. This vector, this is going to be a vector with n entries. N entries. And then we're going to multiply A times this vector. Well, how does it work when we multiply a matrix times a vector? This entry goes to this column. This entry goes to this column. This entry goes to this column. So A times bx is going to be equal to this entry star times this column right here times this entry times this column right here, and so on. These are all going to have m entries, so these have size m. So this is going to be some vector with m entries. But notice we just took a linear combination of the columns of A. This is ABX. And we just took some linear combination of the columns of A. So ABX certainly is in the column space of A because we got it by taking linear combinations of the columns. So that's literally by definition. So this we should know is in Rm. And ABX we already said was an RM, so it could possibly be true. It could be a question mark like this, but we've just shown that it certainly is in the column space because it has to be a linear combination of the columns. So I'm going to circle it. Definitely yes is in col A, right? Another way that you maybe could have looked at it is that if you just call BX Y, then AY is certainly in col A because AY is just, once again, AY is just going to be a vector with these entries that become the weights on the columns of A. So yes, ABX is certainly in col A. Now we're going to do it again, but with BAX. So let's just think about, once again, the sizes of these things, or where they live, where these subspaces live, excuse me. Col A is going to live in Rm, null A is going to live in Rn, col B is going to live in Rn, and null B is going to live in Rm. And BAX, so BA, let's think about BA. So B is n by m, and A is n by n. So this whole matrix is going to be n by n. So X is going to be in Rn, that makes sense. And then BAX is also going to be in Rn because BA is going to take in something that's n by 1 and be equal to something that is also n by 1. Okay, so BAX is a vector in Rn, so we can eliminate col A. We can eliminate null B. Once again, I really have no reason to think that this BAX is going to satisfy A times BAX equals 0. So null A, probably not, no. But col B, once again, if we say Y is AX, then BAX is equal to BY. But BY you should recognize as being a linear combination. This is equal to some vector. This BY is some vector, but how do we get that vector? It's the entries in Y becoming weights for the columns in B. So this is certainly in col B. So take a second to realize that every time we multiply a matrix times a vector, that it's going to be a linear combinations of the columns of that matrix. And so every time you do that, it's going to be something in the column space. Right? So it's got to be in col B. Continuing with number 2, so A is still n by n, B is n by m. And now we have m greater than n, and we want to know about the columns of A, B. So once again, with these types of problems, I think it's really useful to sort of just draw out what A and B sort of look like with their dimensions. So we're taking the product AB. So let's draw A this and B like this. A is m by n, so m rows, n columns, n rows, m columns, and B. And so we want to know about this product. So one useful way that you can think about matrix multiplication sometimes is that matrix times a matrix, you can look at the second columns of this matrix You look at the columns of this second matrix. And in the product, this matrix product is going to be a matrix where you take the first matrix, multiply it by this row. So if we call this A, and we call this B1, B2, dot, 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 BM, this first column is going to be A. So this first column is going to be A, B1, A, B2, dot, 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 A, BM. So let's just check the size of this product. So A times B1 is m by n times n by 1. So this is going to be m by 1. So this is m by 1. So this matrix has m rows. And there's m of these vectors, so there's going to be m columns, which makes sense because A times B should be m by m, right? So why is this going to be helpful? So I want to think about the columns of A, B, this matrix right here. I want to think about the independence and dependence of these columns. And the way I'm going to do that is if I think about m being greater than n. So that means that in this matrix, since m is greater than n, there has to be more, like, this matrix has to be sort of short and wide. So that means that you can't possibly have a pivot in every column. So there has to be some sort of free column in B. So that means that calls of B are dependent. So the columns of B have to be dependent. But how does that help us? So we can picture the columns of B all sort of being in these different directions. So B1 dot 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 BM. But one of the guys in the middle one of the B's has to be a linear combination. Maybe call it BI. One of the BI's has to be a linear combination of the rest of them to make this dependent set of vectors. But when we think about multiplying A by each of them, if they start sort of all dependent and we multiply each of them by A, is it possible that they could all sort of land in an independent way where they're no longer some sort of linear combination of each other? The answer is no. So this linear transformation, the vectors are all going to look different afterwards, but we're still going to have, so this would be like AB1, this would be ABM, but this ABI is still going to be a linear combination of the previous guys. In fact, we can prove it. If BI is like C1, B1 plus dot 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 plus CM, BM, then we have that ABI is going to be A times this linear combination, C1, B1 plus dot 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 plus CM, BM. But then now we can distribute this A over this sum. So this is going to be I'm going to distribute the A over the sum, and I'm also going to pull out the weights at the same time. So I'm going to put the A over the sum, and then I'm going to pull the CI's out to the front. So it's going to be C1A B1 plus dot 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 plus CM A BM. So now we've expressed ABI as a linear combination of the rest of the ABs. So this whole set of the ABs are not going to be they're not going to be independent. So the columns of AB are not going to be independent. They actually have to be dependent. So we'll put this box. So for D, I just want to show you two examples where one is independent, one is dependent, and that'll show that both are possible. So I'm going to let A, so first we'll show it could be independent. So A is n by n, and m greater than n. So A should be sort of tall and skinny. So we're going to do 1, 0, 0, 0, 1, 0. And B is going to be the same matrix but transposed. And then AB is going to be 1, 0, 0, 0, 1, 0. Sorry, we're talking about BA here in part D. So BA is going to be 1, 0, 0, 0, 1, 0 times 1, 0, 0, 0, 1, 0. So this product is going to be 2 by 2. So in the first entry, that's the first row times the first column, that's 1. In this entry right here, it's going to be the first row times the second column, that's 0. In the third entry right here, it's going to be the second row times the first column, that's 0. And then right here, it's going to be second row, second column, that's 1. So here is a case where the columns of BA can be independent. And it's not hard to make a case that the columns could be dependent. The way that we could do that, we can make either of the matrices just the zero matrix. So if we make B, the zero matrix, then we're going to see that BA is going to have dependent columns. Obviously, BA is going to be the 2 by 2 zero matrix. So in both cases, it's possible. I'll let you guys think about on your own what the conditions would be to have to guarantee one or the other. I'll leave it as exercise for you. All right, so now for part E, still have m greater than n, but now we have ax equals 0 has non-trivial solutions. Then the columns of BA can be either independent or dependent. So when it says ax equals 0 has non-trivial solutions, I want you guys to read that and immediately realize that means the columns of A have to be dependent. So you might be wondering, why is that the case again? So let me show you why that's the case. If there's some non-trivial solution to ax equals 0, that means that A times some vector x1 dot 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 xn equals 0. But at least one of the xi's, is not 0. This is what it means to be not trivial. If it was trivial, all of them would be 0. If it's not trivial, that means at least one of them is not 0. So say xj is not equal to 0 in this vector. But we'll keep this in mind. But now let's look at this product. So matrix times vector, we've talked about before, means linear combination of the columns of the matrix weighted by the entries in the vector. So if A has columns A1 through AN, so let's say A has columns A1, AN, that means that x1, A1 plus dot 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 plus x and AN equals 0. And also realize that one of these xj's wasn't 0. So what that means is that we can isolate that xj and say xj aj equals, and then move all of the other terms to the other side. Negative x1 a1 plus dot 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 plus, sorry, these should be minuses because we moved them over to the other side, minus x2 a2 minus dot 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 minus xn an. So we've moved these all over the other side. Realize that this j isn't on this side. It's isolated on this side. And then realize that you can divide by the xj. So aj is negative x1 over xj a1 minus dot 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 minus xn over xj a n. And we said that xj is a 0, so we don't have to worry about dividing by it. But now we've written one of the columns as a linear combination of the other columns because each of these are just weights. So we have one of the columns as a linear combination of the rest of the columns. That means that the set a1 an is dependent. So that was just a little bit of review for why ax equals 0 having not trivial solutions means that the columns of A have to be dependent. So now let's think about BA. So once again, we're going to use the fact that B times A is just B multiplied by each column of A. So BA is just this matrix. B times A1 dot 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 B times A, and BA A has n columns, so this is going to be up to n, and BA is going to be n by n. So BA is just this matrix where each of the columns is B times one of the columns of A. But now let's think about it. So since A has to have dependent columns, for the same reason as we had in part C, if these columns A1 through AN are all dependent, after multiplying all them by B, BA1 through BAN, maybe they're rotated or projected or something, but after this transformation, they're still going to be dependent. Okay, and we showed that in part C. If you weren't sure about that, you want to go back and see why that's the case. But it should sort of geometrically, like let's say I have two vectors on a line. No matter what linear transformation I do to these two vectors, they're still going to be dependent. Like they're not going to end up in different directions, right? So that should make some sort of sense to us. But what this means is that these BAIs are all dependent with each other. So this is going to be our answer. Question 3, we have 3 different transformations. Part A, we want to find the standard matrices for those transformations. So as we talked about in studio last week, the strategy for finding the standard matrix for a transformation is just find T of E1, find T of E2, find the image of all of the standard basis vectors, and the images of the basis vectors, the outputs of the transformation applied to those basis vectors is going to become the columns of the standard matrix. So I'll show you what I mean. So first, let's picture the transformation. So let's picture T. So T takes vectors in R3. Let's say this is X, Y, Z. And the output of the transformation is a vector in R2, which is just X, Y. So you drop the third component entirely, which means that you land in R2. So keep in mind, there's a subtle difference between, say, projecting onto the floor in R3. So that would be like the output is X, Y, 0. So there's a difference between like projecting down onto the XY plane in R3 versus actually like going into R2 and having a vector in R2. The difference is sort of subtle, but we're going to see that the matrices they're going to look similar, but they're going to be different size. So I would encourage you to write down the matrix for this transformation. But T is actually going to leave R3 completely and give us a vector in R2. So once again, the strategy for finding the matrix is finding T of E1, T of E2, and T of E3. And that's going to become the columns of our matrix. So E1 is 1, 0, 0. So T of E1 is just going to be 1, 0. E2 is 0, 1, 0. So E2 is going to, T of E2 is going to be 0, 1. Now T of E3 is not as obvious, but T of E3, remember, is T of 0, 0, 1. And we basically just dropped the third component entirely, so T of E3 is just going to be 0, 0. So that means that A is 1, 0, 0, 1, 0, 0. So each of the outputs became each of our columns, right? So this is A. I'm going to, I guess, leave it over here for our safekeeping. So A is 1, 0, 0, 1, 0, 0. Same process for the matrix, the transformations U and V, which have matrices B and C. So let's do it. So let's picture U. So U takes vectors in R2 and sends them to vectors in R2. So for every vector U, its output is going to be the same sort of length, but it's just going to be rotated. So here T of U is probably like over here. So this is what the picture of the transformation looks like. Everything gets rotated, and that's what the output looks like. So very easy to find T of E1 and T of E2. Do we have to find T of E3? No, because the domain is R2, so we only need to find T of E1 and T of E2. So E1 is this vector 1, 0. So it's very easy to see that T of E1 is just going to be rotated right here. So it's going to be 0, 1. And E2 starts right here. Sorry. U rotates clockwise. I was doing the transformation counterclockwise. But that's okay. That's an easy fix. So instead of T of U being here, T of U would actually be here. And we have to think about E1 rotated clockwise. It's going to be 0, negative 1. And then E2 rotated clockwise is going to end up at E1, or 1, 0. Okay, so B, this column, this column. So let's write it here. Now you could have said, Will, isn't there some sort of formula for rotating? And I would have said yes. But who wants to memorize that formula when we can just use the process of just seeing where E1 and E2 go? You can't mess it up because you forgot it or something. It's this way. It's basically foolproof, right? I like methods that are foolproof. Now for C, we just have to do V. So it's going to be scaling the x direction by 2. So what does that transformation look like? So input and output are both R2. It's going to be easy to think about vectors on the x-axis. So if I'm here, say like x, 0, I'm going to end up at something 5 times as large in the x direction. So that's 5x, 0. And that rule is actually going to work for any vector. So if I'm at xy, the transformation is going to be 5x in y. So how do we find the matrix? Let's write down T of E1, T of E2, So E1 is 1, 0, so that's going to be 5, 0. And sorry, I don't know why I was scaling by 5. It says scaled by 2, so it's easy to fix. It's just 2, 0. This right here should be a 2. This right here should be a 2. And then E2 is a little tricky, but it's 0, 1, so its x component is 0. It's just actually going to stay the same. 0, 1. So C is 2, 0, 0, 1 for scaling the x direction by 2. Once again, you might have memorized this formula, or you might have seen this is what scaling in a direction looks like, but once again, I like methods that are foolproof. So just keep in mind that if you want to find the standard matrix, all you have to do is just apply the transformation to your standard basis vectors, and it's going to work out nicely for you. Okay. All right, so for parts B and C, we have this composite transformation, these two composite transformations. And there's basically going to be two strategies that we can use to solve these problems. The first is just going to be do the same exact process we just did, which is find T of E1, T of E2, blah, blah, blah. And following where they go throughout the whole transformation. The second way that we can do it is just by multiplying the matrices together, sort of in the proper order that represent each of the individual transformations. And it actually doesn't matter which way we do, it's sort of a matter of preference. So we're just going to do it both ways. So for B, we're going to do the same method of tracking T of E1 through T of En. And the second method, we're just going to take the individual matrices and multiply them together. So I'll show you both ways. All right, so for B, we have this composite transformation V of U of T. So it's very important to sort of think about the order in which these transformations happen. So just for example, if I have V of U of T, this is some transformation and I apply it to X. What does this actually mean? This means V of U of T of X. So if I follow the order of what happens, so I plug in my input X, and that goes first into function T, which is evaluated to be T of X, and then that output it goes into the input of U, and that is evaluated to be the output of U, which is U of T of X. And then finally, the output of U, it goes into the input of V, and then we have the final output V of U of T of X. So if you follow the order, first T happens, then U happens, then V happens. So in general, in linear algebra, when we have compositions of functions, we sort of want to read them from right to left. And that's going to be important when we do the matrix multiplication way. Okay? So if we think about this transformation, so first we're going to start in R3. Since T happens first, the input of this composition function has to be in R3. So let's just write that down actually. So the domain of V of U of T is R3 because any input to this function, since T happens first, has to be in R3 because T happens first. And then U happens, and then V happens, and those both go from R2 to R2. So the codomain of this composition function is going to be R2. So overall, this composition function goes from R3 to R2. But that makes sense because T goes from R3 to R2, and then U goes to R2 to R2, and then V goes from R2 to R2. So if we track that overall process, it overall goes from R3 to R2. Okay? So first we're going to take a vector x, y, z. And then we're going to drop its z component, and we're going to end up in R2 at x, y. And then we're going to rotate clockwise by 90 degrees. So So let's call this x. So this is going to be t of x, and then this is going to be u of t of x. And then finally, we're going to scale the x direction by a factor of 2. So one more transformation, still going to be an R2. V of u of t of x is going to be something like over here. So v of u of t of x. Okay. So this is sort of what the picture looks like. So what now I want to do is just do this to E1, E2, and E3. And hopefully we can just sort of track where they go. Okay. So I'm unfortunately going to have to make some room. But that's okay, because we can sort of picture the transformation now. So E1, T of E1, T of E2, T of E3. We have to do it 3 times because the domain is R3. So E1 is going to, it's going to start in R3. So this is E1, E2, E3. E1, E2, E3. So then E1 is going to go here. This is T of E1. And then after U, it's going to go here, which is U of T of E1. And then finally, we're going to stretch it in the x direction by 2, but since it's on the y-axis, that isn't going to change it at all. So it's going to be V of U of T of E1 is going to be right here at 0, -1. Right? Now for E2. So now I'm going to do it in reverse. So E2 is here. So E2 is going, T of E2 is going to be here, and then clockwise by 90 degrees is going to be here, and then stretching the x direction is going to be over here. So we can figure that this would be 2, 0. Now E3 is going to map, so E3 starts here. It's going to map to the origin after T, and then after rotating the origin around the origin is just going to leave it at the origin. And then stretching it in the x direction is not going to change it at all. So we're actually going to end up still with T of E3 is 0, 0. Okay, so for part B, the standard matrix for V of U of T is going to be given by these 3 columns, 0, -1, 2, 0, 0, 0. Okay, very good. So this is how we would use the just follow the vectors method. I guess that's a good way to call it. The follow the vectors method is how we solved part B. Now for part C, we could very easily do the same exact process, but now we're going to use the multiply the matrices method. So we're once again going to do T first, but now we're going to do V, then U. So the way that the multiply the matrices method works is that you take the 3 functions and you replace them by their standard matrices. So the standard matrix for U of V of T first is going to be the matrix for U, which is B, so it's going to be 0, -1, -1, 0. And then it's going to be the matrix for V, which is C. And then finally the matrix for T, which is 1, 0, 0, 0, 1, 0. So all we have to do is just multiply it together. So the important thing is that you just put them in the right order. So it should make sense because once again, if we're going to multiply by some vector x, y, z, one way that we could do this product is first multiply by this, then take this product, which is a vector, and multiply it by this guy, which is going to be a product of a vector, and then by this guy. So the order that the transformations happen is the order that you put the matrices from right to left. Okay. So let's just do this product. So first I'm going to evaluate this. So that's going to be, I'm going to leave this guy -1, -1, 0. So 2, 0, 0, 0, 1, 0. Now this product, 0, -1, 0, -2, 0, 0. So this is the standard matrix for u of v of t. You might be wondering, oh well, it seems like this multiply matrix method seems faster. And a couple of comments about that. I generally prefer the follow the vectors method because I just don't like multiplying matrices together. It's prone to errors. You can mess it up very easily. It could take a while. And also keep in mind that part of the question was writing A, B, and C first. So if you didn't have to do this and it just wanted us to jump to u of v of t, we could have jumped straight to the matrix for u of v of t without finding A, B, and C at all. So just keep that, we could have jumped straight there, but since we had to find A, B, and C, I suppose that finding the matrix for the composition, after having done that, is probably maybe the way to go, because it's not that hard to multiply these matrices, and maybe if you're not comfortable with the geometry of some of the transformation, then you wouldn't want to do the follow the vectors method. But this shows you both ways, and I think this is a pretty good coverage for this problem. I would maybe suggest that you try the matrix, follow the matrix way, multiply the matrices way for this problem, see if you get the same answer, and then try the follow the vectors way for this problem and see if you get the same answer.